Hey, it's me, Brandon. I'm the geology guy. I'm making this series of videos as companion videos for my Geology 101 class. I teach Geology 101 at a community college, and I really enjoy it. And so these videos are specifically meant for my class, to go through the book, but also for you if you're not part of my class. Now, if you are in my class, you're going to need to have this book here. This is called Earth Lab, Exploring the Earth Sciences. And it's not just a textbook, it's a lab book. It's kind of two of them together. And there's really great lessons in here, reading and activities for you to do on such topics as plate tectonics, igneous rocks, metamorphic rocks, atmosphere and climate, landslides, rivers and streams. So all of my videos are going to be formatted based on the chapters in here, as well as additional information that I think is important to understand these concepts and to be able to grasp them. Before we get into geology, though, first we need to talk about science in general. What is science? There's a lot of great videos already out there that have dived into the history of science and the scientific method. And so I'm not going to go into the history, although there's some really great ones. I'll post some links in the description. Check them out. But we do need to talk about the scientific method. See, science isn't just a collection of a bunch of random facts. Science is how we connect those facts together to make them meaningful and relevant and useful. The way we do that is through hypotheses, models, and theories. The scientific method is the collection of processes that we've come up with through historical trial and error, the most logical and concise way of discovering facts, but also connecting those facts together. It all starts with asking questions, making observations, looking at the world around you, and asking why this, why not something else. Something that always drove me as a kid interested in geology was I grew up in the Pacific Northwest, and I'd look up at mountains like Mount Hood in Oregon and Mount Jefferson. These are the places that I went as a Boy Scout, and I would wonder, why are there mountains here? And I'd look at pictures of, say, the Great Plains and think, why are there mountains here in Oregon in the Pacific Northwest and not in, say, Kansas? Well, geology can help answer those questions through the scientific method. As we ask these questions, we need to make empirical observations. When we make empirical observations, what we're looking for is something that describes a phenomenon or describes a characteristic of something. We're looking for unbiased, unopinionated, objective facts, dimensions, weight, color. It's important to distinguish observations from guesses, interpretations, conclusions, inferences, and then we can classify and categorize the data. This helps us make generalizations, formulate laws, which are a collection of observations. It also helps us summarize many observations. Once we've gathered enough data, we begin to formulate a hypothesis, an educated guess. Not a wild random guess. It's based on the data that we have at hand. And it is an attempt to explain why or how something is the way it is. A hypothesis attempts to connect various circumstances with a common underlying and governing principle. A good hypothesis must be able to explain all of the current data and make predictions about future data not yet collected. A good hypothesis has to be falsifiable. Now, falsifiable doesn't mean that it's false, it means that it could be false, meaning that you can test it. So a hypothesis that you can test and that somebody else can repeat and duplicate and attempt to disprove through testing is falsifiable. If you make a claim about something that nobody else can reproduce, nobody else can test, and nobody else can attempt to disprove, then it's not falsifiable. Let me give you an example. I have a dragon living in my garage. Seriously, why don't you come on over and take a look. Now, when you get here, you're not actually going to be able to see my dragon because my dragon's invisible. And you might think, well, I can just take a bunch of sand or flour or something and dump it on the dragon so that I can at least see the outline of the dragon. That would be pretty cool, right? But see, the problem is you're not going to be able to do that either because my dragon is incorporeal. See, that's an example of non-falsifiable. You can't test it. So if you have a testable, falsifiable hypothesis, other scientists can take that hypothesis and put it to the test. You yourself can put it to the test, multiple tests. The more times you test a hypothesis, and are not able to disprove it, the more that hypothesis gains strength, gains credibility and validity. A hypothesis that is refuted by additional testing or further evidence needs to either be rejected or revised. Now, a hypothesis that has undergone testing after testing after testing and continues to withstand the test of time, continues to not be disproven, gets strengthened and more strengthened, eventually graduates to what we call a theory. See, in the scientific community, there's no such thing as just a theory. The way we use that colloquially, we usually mean, oh, it's just a guess, just a theory. But in science, a theory is actually something that's very strong. A theory is the highest level that a hypothesis can get to. The more we test it, the more we have trust in it, the more credibility it has, to the point that it becomes what we call a theory. So theories such as the theory of evolution by natural selection, that is an explanation that is testable and falsifiable and has been tested over and over and over again, to the point that we have now called it a theory. Does it mean that it's true? No. But it is more likely true than other hypotheses that have come along. Another theory is the theory of plate tectonics, which attempts to describe how different portions of the Earth shift around, which we will get to in more detail later. One last thing I want to talk to you about with the scientific method are models. You've probably seen little models of, model car made out of plastic or wood, model car, model boat, model airplanes. They basically show a miniaturized version of the actual real-life thing. Scientific models are similar. They're simplifications of real-world phenomena. Models can help us better understand natural phenomena. A model may isolate a particular aspect of nature from the rest of processes and the rest of nature going on around. A model can help us give the appearance that time is speeding up or slowing down so we can understand processes. For example, the process of mountain building in geology is a very slow, multi-million year process. But through models, we can develop a model that speeds up that process so we can see how things work over such long spans of time, but we can watch it in a span of time that we can actually witness. Models help us understand a complex set of processes in a better, more simplified way. Models can be used to test hypotheses. An accurate model will yield the same or very similar results to the empirical observations of the processes that model is representing. So to make sure that a model is accurate, it first has to be tested against actual observations before then going on to predict observations that haven't taken place. Some examples of models that we use in science that we're going to use in this class even are maps. Alright, I hope you'll stick with me through the rest of this series. We're going to learn all about plate tectonics and maps and different types of minerals and rocks. We're going to learn about processes that shape the earth through earthquakes and mountain building. We're going to learn about other processes like rivers, streams, and erosion, groundwater, landslides. Geology is one of those topics that I believe everybody likes, but not very many people really care about. So it's my hope that I make some of these principles about geology fun, interesting, and understanding to everybody. Thanks for watching. I'm Brandon, the Geology Guy.